Hey everybody, Samuel Singer here. It's my pleasure to introduce our speaker for this evening. Dr. Brian Keating is an astronomy professor from the University of San Diego.
University of California, San Diego.
University of California.
Half the price
San
of
Diego.
USD, yes, half the price tuition.
He does research in cosmology, and he's here to tell us all about it. Brian, thanks so much for being here. And
Pleasure to be here.
Take it away.
Thank you. Thanks everybody for coming out on this unusually stormy night in Wyoming, but it's a pleasure to be here. I love coming out here. Brought my film crew with me, so that's great. Special thanks to Samuel for getting in touch, and Brad actually is the main conduit, the matchmaker, so thank you so much. And of course, thank you to the Adlers for hosting us at this wonderful location. This is astronomy paradise. You've got everything, including the imaging systems that I crave. So I hope to make a good impression on you, so you'll invite me back. I'm going to talk a little bit about the cosmic adventure that led me to write a book, which will be given away, I guess, to some of the members of the Wyoming Stargazing Association, a group that I hope to not only come back and visit with, but maybe team up with for some imaging projects from research projects involving the type of science that I do, which is polarimetry, which is actually accessible to amateur astronomers now for the first time. And it's a way that you can actually make contributions not only to the study of celestial phenomena, but actually what's called fundamental physics. So the study of particles, forces, and fields, and the determination if Einstein was ultimately correct that there could be a grand unified theory that couples together all the forces of nature into what's called a theory of everything. And if so, if that were to be true, we could test the veracity or lack thereof by using polarimetry, and even amateur astronomers are doing these types of things. So the book that I wrote is called Losing the Nobel Prize, so spoiler alert, anybody hoping to meet a Nobel Prize winner, be sorely disappointed. But I always thought when I would read these books, so the book is available for your choice of hard and soft covers, but whenever I read a book and it was a hardcover, the dust jacket would fall off. And it always got me thinking, why do we need a dust jacket? Like, why is there so much dust falling on people's books? Like, and who needs this thing? Like, you don't have a car dust cover that you have to take off or to put on all the time. And so, but I soon came to realize that the dust that is covering our books is also covering our cosmos. And that, in fact, led to the juxtaposition of me losing the Nobel Prize, perhaps, and also this book cover that you see in the background. And books actually are judged by their covers, as none other than the first astronomer to ever use a telescope, Galileo Galilei, found out himself in one of his books that I'll show you in just a little bit. The first book, the SIDEREVS Nuncius, used this little tiny telescope, a refracting telescope with about a 1.5-inch aperture, which is nothing compared to what even some of your finder scopes will probably allow. And instead, he was able to glimpse something that caused him to change the paradigm of how we view the entirety of the cosmos. So it's really phenomenal that this tiny little telescope could be a crowbar. It could be a lever that literally moved the entire Earth away from its position that was assumed to be the center of the universe for millennia before Galileo's first observations. And he did it using this book, or presented it in this book, which was self-published. It was published without peer review, and that will be relevant later on as we get into it. But it was written in Latin. The language of this is Latin, very different from his final book, or second to last book, the one that got him home imprisoned, house imprisonment. And that was written in Italian. And there's a big difference between a book written in Latin and a book written in Italian. Not that I could write either one. I write mostly in English, except for some equations. But in the book, published exactly 410 years ago this year, in January of 1610, Galileo observed that the planet Jupiter was accompanied by 4 stars, which he realized that they were satellites orbiting as viewed edge on from the Earth perspective. And they were moons of the planet Jupiter. So he quadrupled the number of moons that we knew about in the entirety of the cosmos by one single astronomical observation, which also destroyed the notion that the Earth was the center of the solar system. For these moons were clearly rotating and orbiting around the planet Jupiter, not the planet Earth. So it could not be reconciled with the Aristotelian Ptolemaic version of the universe. As I said, he published this book, the SIDEREVS Nuncius, the Starry Messenger. He rushed it to publication, and just 2 months after writing making these observations, in which he also observed craters on the moon. And just recently I got asked to appear with none other than Captain Kirk, William Shatner, on an episode of Unexpected, which hopefully will air before the end of the year. And my role is to explicate exactly why the moon is so important, both to life in the universe, but also to astronomers, and how we might use the moon's surface to actually do astronomy. So someday, Wyoming stargazing might have a base on the moon. We can wish, right? We can hope. So if you look up in the night sky in the winter, you guys all recognize this little object. You guys all know, I don't have to tell you, it is not a constellation. It is an asterism, which in Japanese is pronounced, how do you say this in Japanese? Any students? Subaru. The seven sisters. But what's wrong? How many sisters are here? How many stars are here? There's only six. There's only six. And in fact, they thought there were about 6 stars. But when Galileo looked at it, he observed that there were an uncountable number of stars. In fact, what he did was quite beautiful. And actually, this guy, Edward Tufte, he actually claims that this was the first use of data science in scientific visualization. Because what Galileo did is he plotted stars that you could see with the naked eye as these open kind of stars of David. And then he plotted the stars that you could only see with the help of a telescope as these filled-in stars down there. And he said that there are basically an uncountable number of these such stars, and that was the nature of the Milky Way galaxy itself. That the Milky Way galaxy was composed entirely of stars that the eye was too feeble to resolve, but if he had a bigger telescope, he thought he could resolve every star in the Milky Way, or every pixel of light, into individual stars. We now know that that was wrong, but what he says down here is kind of telling about scientists and the way that scientists think about their data and how precious it is. He says what was observed is the nature of the Milky Way itself, which with the aid of the spyglass, which is what he called the telescope, may be observed so well that the disputes for so many generations have vexed philosophers are destroyed by visible certainty. So he's making an argument that just using your eyes, you can prove something almost mathematically. And of course, we know now that when such things are done, there's a ripe possibility for what's called confirmation bias. So I call this Galileo's biggest blunder. Einstein's biggest blunder actually was the so-called cosmological constant, which turned out not to be a blunder, and actually is claiming it was a blunder is the actual blunder, but we won't get into that. Nowadays, if you happen to have Mount Palomar available to you, you can see that even the glowing light around the Pleiades is not even visible as stars. It's a glowing reflection nebula composed of gas and dust left over from this stellar creation that took place. Here's a zoom in using the Hubble Space Telescope of the star Merope down there. And you can see these knots here. These are 10 times larger than the scale of our solar system. And they have enough material to form entire solar systems. So this led astronomers later on to also kind of have a new vision of what the universe was composed of. And to say that there's actually a type of other material that they didn't quite understand and has come to plague and vex astronomers ever since. So what Galileo did with that new model where the Earth was the displaced from the center of the solar system is he published another book called The Dialogue. And the dialogue is written in this beautiful form as a conversation between 3 different characters, one of whom is called Salvati, which means like the savior, and that's Galileo. He's putting his words into the character of this guy named Salviati. And then he put the words of an interlocutor, someone who's just kind of an educated layperson, and that was another character. And then the Pope, he put in the name of a character called Simplicio, the simpleton. So that wasn't so, that would be like, you're calling your funding agency a simpleton. They don't react well to that. And in fact, they did put him under house arrest for the final 9 years of his life. It wasn't so bad. Trust me that Ghislaine Maxwell or what's his name, Bernie Madoff would kill literally to be in the house imprisonment in a villa in Italy where he did ride out the last few years of his life. So Galileo's tiny little telescope could really only see out to the realm of the actual nebulae in our galaxy. So blown up stars, gas, and dust in our galaxy. And it could see things on Jupiter and around Jupiter, but that was about it. We're going to see a varying number of these space-time diagrams, if you will, that show things progressively farther out from the Earth. I always show the Earth, there's no reason to show the Earth with the northern hemisphere on the top, but this book my book takes place partially in Antarctica, so out of prejudice towards Antarctica, I put it that way. Upside down, right. Now, it didn't end there, where scientists confused dust for other properties that they wanted to see in a certain way. So about 70 years after Galileo, a man named William Herschel, operating a Leviathan 40-foot long telescope in England, made a map for the first time of the Milky Way galaxy. And what he did was put the Milky Way galaxy center located on the sun, basically on our solar system. So the Earth, it was then thought, was no longer the center of the solar system, but at least the solar system could be the center of the universe, which was the Milky Way galaxy. Turns out the reason for this can be explained, again, by properties of dust. Dust has three primary functions in astronomy that are pertinent to what I'm going to talk about today. The first thing that dust does is it diminishes the intensity of light. When you look through a dirty window, a dusty window, the light appears dimmer. It also makes the high-frequency blue light scatter out of the field of vision. So light that's remaining appears more red. So dust is considered a reddening source of what's called reddening. And then it also can polarize the light source as well. And these three phenomena come together throughout the history of the Milky Way observations. And any type of astronomy that's done from the Milky Way until we can get outside the Milky Way will have to contend with these pernicious effects of dust. So now we can understand why Herschel centered the Milky Way on the Earth and the solar system that we inhabit. And it's kind of like if you're a pilot flying in a plane and you're inside a cloud. We pilots describe that as being on the inside of a ping pong ball, because no matter where you look, you have equal surface brightness in all directions. And your brain interprets that as you being in the center of something because your visual line of sight ends at a constant distance isotropically, all directions that you look. So even though the Earth is way out over here, we thought we were at the center just as if you were in this cloud, which is not shaped like a spherical ball or spherical cow, nor a spherical cloud. It would appear that it's spherical because of these properties of scattering. This is scattering by water vapor, but that's the general idea. So now, of course, we know, and you've probably all imaged these various objects in our galaxy, which stretches some tens of thousands of light years vertically, and then tens of thousands of light years in radius as well, populated by other things called globular clusters, which also played a role in the determination that the Milky Way is not centered on the Earth, and we're also plagued by the observation of dust. I won't get into that here. I describe a little bit about that in the book. And then the question in the 1900s turned to these interesting objects, which if you saw the Orion Nebula and you saw M51, you might think they kind of look the same. They have similar types of appearances. I mean, these two almost look like mirror images of each other if you're not color coding them. And this is obviously Hubble telescope images or very wide field, very high resolution images. But to the types of technology that were available in the early 1900s, they basically thought they were identical. So there was a question, how could we resolve these literally and figuratively to understand the nature of what these objects were? Are they other universes, other galaxies? Or are they just nebulae like Galileo had observed? And so that fell obviously to Edwin Hubble in the early 1920s to do observations, which I love this picture, and I had a great deal of trouble getting this plate from Mount Wilson, getting a reproduction of it. I don't actually have the plate. That would be pretty valuable. But they did let me reproduce this. And what I love about it is it shows the human side of astronomy. It shows, a few things that were interesting. It shows that astronomers can be wrong. So this is Hubble's image of M31, the Andromeda Galaxy. And then you see up here, you see a couple of chicken scratches over here. And then you see 6th of October, 1923. And then you see over here, there's an N, and then it's crossed out in red. And then underneath it is written Ver, as in variable star, not a nova. So a nova would flare up like a supernova, but these were to be, or he thought it was an ordinary nova the first time he saw it. Then he saw it was repeating periodically, what's called a Cepheid variable star. And from the properties of the Cepheid variable stars, he was able to determine how distant the Milky Way galaxy was from the Andromeda Galaxy. And it turned out to be millions of light years. It actually was much farther away than he actually thought, or he overestimated the distance of it by a factor of 7 because he didn't take into account that there's dust both in the Milky Way galaxy that diminishes the light and makes it appear further away than it actually is. And there's also dust in the host galaxy of the Andromeda galaxy. And both those effects made the light more dim, more red, and affected the color resolution of these photographic plates is less sensitive in the red back in the 1920s. So that was a kind of a double whammy that made him think that this thing was 7 times farther away than it actually is. So he would have imputed a distance of millions of 7 million light years, say. We now know it's about 2.5 million light years away. Here's what it looks like by the Spitzer Space Telescope. And you can see all this glowing stuff is dust. So there's dust in our galaxy. There's dust presumably out where this thing is. And there's dust in the other Cepheid variable networks that are inside and embedded inside of the Andromeda galaxy. So these were all stepping stones to understand the scope and scale of our universe. And they're all plagued by dust. So we're going to fast forward from Galileo's time about 400 years to the 1960s, when these two astronomers, Arno Penzias and Robert Wilson, were using a telescope that looks nothing like Galileo's. This is a microwave feed horn antenna located in, of all places, New Jersey, which I'm a New Yorker by heart, so I wouldn't, it's hard for me to give credit to New Jersey, but still I have to give it where it's due. And they observed this uniform glow of microwaves in all directions. That was later called the cosmic microwave background, and they, 13 years later, won this particular prize that's attracted a lot of attention, called the Nobel Prize. We now know that the microwave background isn't uniform at all. In fact, it's good that it's not uniform, because otherwise we wouldn't be here. The fluctuations, which are imperceptible to the human eye, obviously, because these are microwaves, not visible light, but they trace the local properties and the early universe. How dense was it? How hot was it? How much dark matter was there? How much dark energy was there? What are the properties of those individual components and species in the early universe? And this is a snapshot of the infant universe 380,000 years after the formation of the elements, called the Big Bang nucleosynthesis era. So this is heat, and there's imperfections in the heat. And those imperfections are gravitational fingerprints of the matter distribution in the early universe. But you might still ask the question, where did those imperfections come from in the first place? Why isn't the universe completely smooth, homogeneous, and isotropic? And that's the question we are trying to answer nowadays with the telescopes that I'm building in Antarctica and in Chile. And that's to understand what happens beyond the realm of the planets, beyond the realm of the Pleiades, beyond even the Andromeda galaxy, the Hubble Deep Field, the epoch of reionization, as it's called. And this surface is existing at a time about 380,000 years after the Big Bang. Now, we don't actually know. In the book, I put, the Big Bang could have been time equals 0. We actually don't know if it was time equals 0. Namely, if there was a time that preceded the origin of the elements, if you could ask the question, what happened the Tuesday before the Big Bang? Does that question even make sense? Those are some of the questions we're attempting to answer with the types of projects that I'm involved with and I'm going to talk to you about right now. So where do these fluctuations come from? First of all, they're incredibly small. The average amount of fluctuation, if you take a bowling ball and you were to zoom in on the surface of the bowling ball, it would have fluctuations at the tenths of a millimeter. So hundreds of microns, unless it's my bowling ball, which has a lot of dents in it from dropping it on various things. But that level of smoothness, if you will, or roughness compared to the radius of the bowling ball is far, 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 far rougher than the amount of fluctuation in the microwaves that we see compared to the average amount of microwaves that we see. So that level of fluctuations is tiny, but it's not 0. In physics, you start asking questions. Something should be 0, but it's not. Why is it not 0? If something should be really big, but it turns out to be really small, you start to wonder, what is the fundamental reason for that? So a set of theories came about in the 1980s called inflation. Inflation provides the energy to cause the universe to start expanding. It provides the bang in the Big Bang. It is a theory that marries together concepts from particle physics, from the physics of the ultra small, the quantum network of fields, energy, forces, uncertainty, and fluctuations, and says that the pattern of fluctuations that we see in the cosmic microwave background are the result of quantum fluctuations in something called a quantum field that existed a trillionth of a trillionth of a trillionth of a second after time equals 0, if you will. and only had to last for a very short amount of time to make the irregularities that we now would know would grow into galaxies, clusters, stars, planets, people, etc. But to prove it, or to get more than just circumstantial evidence, we realized we had to look at the third and least appreciated property of light, and that's called its polarization. So the intensity of light is how bright it is, how many photons per second you're getting. The color of light is its spectrum, and it can have a spectrum from radio waves to gamma rays. But the polarization is what is the orientation of the electric field of the light that you're receiving. So most of our senses rely on the fact that we can't distinguish polarization, but there are animals that can. There are bees that can. There's actually types of crystals that the Norwegians and Icelandics, the Vikings, are said to use to navigate based on the orientation of the light from the sun reflecting off of either the clouds or the ocean. And the sensation to the human eye is completely negligible. We have a tiny bit of polarization sensitivity, but very, very little, which makes it the least familiar of these three properties. We see colors, we perceive intensity, but we don't perceive polarization. That is, in my opinion, why it's so unfamiliar to most people. If you're in California, you have polarized sunglasses everywhere you go, because the light that reflects off the ocean is going to be preferentially polarized, even though sunlight itself is not polarized. So light will come in from the sun in this direction, bounce off of these waves here. This is at Scripps Institution of Oceanography. My office is about here at UCSD. This is the famous Geisel Library, which is named after Dr. Seuss. And say you have light that's reflecting off waves on the ocean. You can actually use the properties of polarization to determine properties of the water itself, how salty it is, based on the interaction of unpolarized light with matter. So when matter and light come together, polarization can be produced, and it can tell you properties that you would otherwise be blind to, literally blind to. And so theorists in the 1980s, including a mentor of mine by the name of Alexander Polnareff, who had emigrated from the Soviet Union to London, he made a prediction that if inflation had taken place, we don't know if it did, we don't know back then if it did either. If it took place, we did know one thing. There'd be waves of gravity. In an analogy to waves of light, you can have waves of gravity anytime you have matter that's in motion. You can have the opportunity for gravitational waves like LIGO detected not too long ago, but from the Big Bang itself. Those waves of light, like the waves on the ocean surface, can create a special type of polarization. This twisting, swirling, curling pattern of polarization that we call B-mode polarization. It was not my choice of names. But it was my choice to build an experiment called BICEP, and its successor called BICEP2. And BICEP was an acronym. It stands for Background Imaging of Cosmic Extragalactic Polarization. And there's currently a fourth generation that's in operation. But the concept was very simple. Build a telescope like Galileo's spyglass that's as simple as can be, that has no opportunity for reflection, that has no mirrors, no diagonals, no Naismith focus, no blah, blah, blah. Instead, it just goes straight through as an ordinary refractor with a very wide field of view. Field of view is about 30 degrees in one of the latest incarnations. Instead of using optical glass like Galileo had, he used the finest glass he could find, but still it had a lot of defects and aberrations. We used just ordinary high-density polyethylene. So we used just the same material that milk cartons are made up out of. Instead of using his eye or our eyes, we use these types of detectors called superconducting electronic sensors. And these superconducting detectors operate at 1/4 of a degree above absolute zero. So we cool them down with an isotope of helium called helium-3. It's helium with one neutron removed, effectively. It's a regulated, very tightly regulated commodity. It's very hard to get. And these detectors, you can kind of see a little pattern on it, an XY kind of grid. That makes them polarization sensitive. So this thing can detect intensity, it can detect polarization, and it can do so close to absolute zero because the signals that we're looking for are a fraction of the size of the fluctuations that I showed you before. They're incredibly minuscule. This is what it looks like when we built it before we shipped it from California down to the South Pole, Antarctica, where we're going to go on a little travelogue right now. And this telescope is only about 10 feet tall, and the aperture was only 12 inches. So we don't need to have aperture fever like we amateur astronomers always have. This telescope is, half the size of some amateur astronomers that I happen to know. This telescope, unlike an amateur telescope, has to be cooled way below what you would use an amateur CCD camera, down to almost absolute zero. It's minus 454 degrees below zero Fahrenheit. And unfortunately for me, I couldn't take it to leave it in San Diego or even in California. The seeing is not good enough. Even in California, we have Mount Palomar, Mount Wilson. Instead, we took it to the driest, highest average elevation continent in the world, which is Antarctica. Most people know that Antarctica is a continent, but they don't understand that the South Pole itself is almost 10,000 feet above sea level. So it's kind of like being on an icy plateau on a mountaintop. So you get the benefits of being about a third above the atmospheric water vapor and oxygen content. So it's a little hard to breathe. It's a little bit higher than we are here in Jackson Hole. And also the cold temperature makes it, as it happens here, I'm sure you're familiar with the concept of being too cold to snow, right? That sometimes you'll have a ski report, you'll be bummed it's not going to snow because it's too cold. So now we took it to Antarctica. There you have to get all these pieces of clothing. The pieces of clothing that we take down there are all shown in this image here. You get 2 big bags you can bring down with you. If you're staying for the whole year, somebody has to do that to take care of the telescope, to fill it up with liquid helium. We have to pay somebody to stay an entire year of their life effectively there, because no planes get in or out after the beginning of February, and they don't get back in again until November. So for 6 months, it's completely dark, and for that compensation ranges from about $70,000 to $80,000. And we always joke you only have to work for 1 night. So that's. Now we get there, they got there 100 years ago in boats. It took weeks, and they had to park on the coast of Antarctica for 6 months or 9 months and wait out the winter and then start off for the South Pole. We fly in a cargo plane that looks like this. Here's the accommodations inside the plane. When you get there, you actually see that this is a place for astronomy. There's actually a neutrino telescope located under the ice over here called IceCube. There's a cubic kilometer of ice as its particle detector of neutrinos. There's a 10-meter diameter telescope, the same size as the Keck telescopes, and that's called the South Pole telescope. And then our BICEP telescope, this is the reflective screen. It's basically like an optical baffle, kind of like a dome for the telescope, but keeps the emission from the South Pole away from the imaging sensors that I described earlier. You got to take a selfie when you're down there. And this is where we stay. It's a $100 million station built about 10 years ago, 13 years ago, I guess it is now. And you get a room in one of these little bungalows there, which is actually a little bit smaller than a prison cell in California. You can actually touch both walls simultaneously. You have a little tiny bed up here. You have drapes, and it's light out when I'm there. It's light out. It's the summertime, 24 hours a day. So that's what that looks like. The telescope is up here. Again, the telescope is actually in here. It's in this building here, so you can actually wear a t-shirt in there and you're just as comfortable. This is the most important building at the South Pole, though. That is the outhouse. You don't want to get away with that. So we set out to detect these twisting patterns of microwaves, and lo and behold, we did. On March 17, 2014, we announced that we were detecting the swirling pattern of microwaves, which would be indicative of the universe originating in what's called the inflationary scenario. And the inflationary scenario comes concomitantly with what's called the multiverse, which is that the universe is not the only cosmos that there is. That actually, if you look and you could detect it, there would be an infinite number of universes. So everybody around the world was excited about this. It was on CNN Live. We didn't have any reports from the South Pole because it was winter there. And it was seen on the front page of the most important newspaper of record, the San Diego Union Tribune, but also in the New York Times, The Economist, and elsewhere. And still, in the back of our minds, we were always nervous about the scenario that Galileo had overlooked. And that was whether or not what we were seeing was what we thought we were seeing. We first started to worry back when we were looking at the data analysis if what we were seeing was what we really wanted to see, in both senses of that. Namely, we wanted to see it because we were curious about the nature of the early universe, but we were also, at least in my case, thinking if we did detect it, we would win a Nobel Prize. And because it would be equivalent to discovering the earliest possible evidence for anything in the history of the universe, from particle physics to astronomy to cosmology. So it was really this theological, philosophical, huge breakthrough, which if it had panned out, again, spoiler alert, I want to remind you what dust does. It makes things redder, dimmer, and more polarized. Now, what is the nature of the dust that we ended up having to retract our claim based upon? It's actually not too dissimilar from the candle smoke that gets emitted when you snuff out a candle. And that's not too surprising because the candle is made of cotton or some kind of wick. The candle itself has carbon in it. It's from the fatty acids that make up the wax. And those are all byproducts of nucleosynthesis within stars. And when stars die, they emit fumes and ashes as well. The ashes, here's the process of supernova detonation that leads in some cases in type 2 supernovae to the formation of copious amounts of dust. So when stars explode, when they end their life after of a certain characteristic class, some of them will explode in a supernova, and they'll produce in that supernova explosion fragments of the formation process that leads to eventual coagulation and formation of solar system body objects, not dissimilar from the meteorites that you'll get with each copy of Losing the Nobel Prize, except on a much smaller scale. And then these can be magnetized, and they can be sensitive to the magnetic field of the Milky Way galaxy, and those can get aligned in the Milky Way's magnetic field and reproduce the twisting, curling pattern that we were looking for in the first place. So here's a glamour shot of one of the meteorites that you'll be getting. Here's a spectral analysis that one of my friends did on a meteorite sample. And you see it's mostly made of iron. It's 82% iron. And then it's cobalt, nickel, and then trace elements of everything else at the 9 to 10 parts per million. So it's almost 82% iron, and then cobalt makes up about, with cobalt and the other heavy elements. So this thing is very magnetic. So if you put it next to a magnet, it will stick to it. It's very permeable. And so that means it can get aligned in the Milky Way's magnetic field and essentially mimic the exact signal that we were looking for. So instead of looking at the universe and seeing this pristine image from the Earth all the way back to the Big Bang, we instead see a smoggy, foggy, sooty image instead, much more like driving in Los Angeles. And if you look and think back to this is a famous pale blue dot picture, which I got in the book, reproduced in the book. So when Carl Sagan wrote this little poem, this is on Valentine's Day 1990, they turned Voyager 1 and took a picture of the Earth, and he described it as, if you look at this picture, you see a dot, and that single pixel is Earth. And he says, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. This is pretty poetic, but it's actually true, how dust is really, without dust we wouldn't exist. The iron in our hemoglobin molecules in our blood comes from that same process that produces the meteorites, that produces micrometeorites and dust that contaminates our measurement. So it's not all bad, otherwise we wouldn't be here. But it does have a certain effect on another type of metal, and it blew away any chance that I had of winning a Nobel Prize. So we started thinking about how could we do better next time? How can we build a better project, upgrade what we're looking for? And to do it, we and our colleagues have invented something called the Simons Observatory. And it's a team of 240, it's actually close to 290 now, researchers on all 6 and 7 continents. So that's our funding agency. It's actually almost entirely funded by the Simons and Heising-Simons Foundation. And what is it? People want to know, what is it? So to get rid of the dust, we are building a giant super sucker, a vacuum cleaner to take into space. And by doing that, no, you guys don't believe that. We can't do that. Instead, we have to build a certain kind of telescope that will see dust as well as the cosmic signals, and then remove the cosmic signals, or remove the dust signals from the cosmic signals. So if you imagine the total signal you see is the cosmic signal plus dust, you make another measurement just of the dust, then you subtract the dust measurement from the cosmic signal, and you're left with, hopefully, just a pure cosmic signal. Okay, I'll finish up really quickly. So the Simons Observatory is based on a big telescope, as well as 3 small telescopes. And they are used to make measurements both of the cosmic microwave background and also of the dust signal itself. So we do that using multi-frequency coverage maps, and we use very advanced modeling of how the galaxy behaves based on these multi-frequency images that we make. And so this telescope is under construction. It's 6-meter diameter primary and a 6-meter diameter secondary. It's a very unusual design, meant to minimize the polarization systematic effects that we would otherwise incur. Then we also have 3 small telescopes called the small aperture telescopes that are kind of like the BICEP telescope. They're refracting telescopes. And I'll finish this with a call to action to check out my YouTube channel if it survives this amazing storm, where I'm having interviews with people from all over physics and astronomy, including Nobel Prize winner Adam Rees, who won the 2011 Nobel Prize for discovery of dark energy. And he was on the show recently, and we're hoping to have a series of debates. This year is the 100th anniversary of the great debate between Shapley and Curtis, and we thought it's a great time to have a new series of debates about the fundamental nature of the cosmos, from the very biggest scales that I study with my colleagues, all the way down to the smallest scales of the fundamental nature of whether or not there is potentially a theory of everything. So with that, I say thank you, and hopefully we won't get hit by lightning anytime soon.